welcome to a new Voltlog. Today we're going to take a look at something interesting. As you can see here on my left, I have this huge antenna and radio assembly, which by the way weighs approximately 25 kilograms. So as you can imagine, it's not easy to handle and move around in my small lab. In fact, it takes up most of my bench, so I'll probably do this teardown on the floor where I have more space to move around. This antenna is called Gigabeam WiFiber, and it's manufactured by a corporation called Gigabeam Corporation, which apparently went bankrupt in 2010. The system is supposed to act like a transparent access point, offering gigabit links where fiber is impossible to install. The radio operates in the 71 to 76 and 81 to 86 GHz radio spectrum bands, and the modulation format is BiPhase Shift Key. They have a transmit power of 20 dBm, which translates to 100 milliwatts, and that is not really a great deal of power, but the antenna has a large gain of 50 dB. The system takes a gigabit fiber input, and on the other side, from the receiving antenna, you get a gigabit fiber output. I have a pair of these. One of them is broken, and I'm going to attempt to find the fault and maybe fix it. I'm hoping the problem is somewhere in the power section, because that will be an easy fix. Otherwise, I don't have a spectrum analyzer to take a look at the different RF stages, so a fault in the RF section will probably mean I can't fix it. Anyway, in this video you're only going to see the teardown, but that should be interesting on its own because I expect to see lots of RF magic inside and interesting system design. On the side of the radio module we have a couple of ports. This one is the power input port, which takes 48 volts DC. This is the fiber link port. This is the Ethernet port, used for management only, I believe. And we also get an RS-232 port for command line interface to the radio operating system. I think we've seen enough on the outside, so I'm going to proceed with separating the radio from the antenna and then opening the radio enclosure. So it looks like the radio assembly, which is this box right here, is connected to the antenna assembly using 4 screws, 2 on this side and another pair on the other side. So I'm going to remove those and see if I can separate the radio assembly. Now I'm going to try to lift the radio assembly. Oh, and it is very easily disconnected. It seems they have this very nice feed through going from the radio assembly to the antenna assembly. So now that I have all the screws removed, I'm going to attempt and separate this top cover from the radio assembly and see if we can get in. There must be some kind of O-ring or some kind of sealant to ensure water doesn't get in. And it seems I was right, there was an O-ring on the outside of this top cap, and we get full access. So starting from the main die-cast housing, which is right here, we have the connectors, and they are each going through cables to the main board. So we have the yellow cable, which is the RS-232 serial port, and then we have this gray cable, which is the actual 48 volts DC power input. We also have this Ethernet cable, which goes to the main board, and that is the Ethernet control port. Right here we can see the two fiber pigtails which also go to the main board, and we have this LED or light bulb indicator. I'm not sure because it looks rather big to be just an LED indicator. And we'll move to the right to the main board, and right here on the main board we can immediately spot some things like the power input. It seems like we have a small secondary board which goes underneath the main board, and here is the power input, and I'm almost certainly we're going to have some DC to DC converters on this board which are feeding power to the entire main board. Here we have the fiber pigtails going into this fiber optics module, and on the right side we can see the Ethernet port and the RS-232 serial port going into these RJ45 jacks. And one other thing, we can immediately spot two important LAN patterns on this PCB, BGA LAN patterns. I'm almost certain when we flip this board over we're going to find a processor and an FPGA on this board, because usually there is an FPGA involved when doing this kind of digital modulation / transmission. So as I was telling you earlier, this is the main board, and as we can see here in the seal screen, it is labeled as the radio control module and it has an assembly number. Let's try to identify some of the components on this board, and I'm going to start by first saying that we can clearly see this whole left side of the PCB is reserved for mostly power supply stuff, because these capacitors and inductors combinations are dead giveaway. These are DC-DC converters, and we can see one over here, another couple smaller ones in here, and towards the bottom side of the PCB we also have 4 or even more DC to DC converters. This is the SMT4004, and it's an integrated programmable voltage manager IC which can monitor and control up to 4 independent supplies. And we can see that easily with the components surrounding it. We have mainly 4 large DC to DC converters which can be identified by these 4 inductors. We can also see the shunt resistors used for measuring and monitoring current, and also these 4 MOSFETs which are used for control. Also on this side of the PCB we have a reset switch, which at the moment I don't know what it does, but I'm sure I'll find out later when I start to debug on this PCB. On this lower right side of the PCB we can see some SDRAM and some flash which will be used to hold the operating system files for the embedded processor that we can clearly see by its BGA LAN pattern, and will be soldered on the other side of the PCB. Right here we have the Maxim DS1339C in combination with this supercapacitor, and this circuit is obviously used for timekeeping on this board, and also we can see that it is placed in close proximity to the application processor on this board. This IC right here is the PI49FCT3803 from Pericom, and it is a 1 to 7 clock buffer targeted at networking applications. This chip basically takes the input clock from this oscillator, which is placed in close proximity, and buffers it to 7 outputs, maintaining a low skew between outputs. This cable right here is an output going to the LED indicator present on the die-cast aluminum case. Moving up on this PCB with this IC right here, this is the ICS601, and this one is also a clock multiplier, but in this case it is a 1 to 5 clock multiplier, And this chip obviously takes its input from the close by crystal oscillator and produces 5 clock outputs which are buffered. Right here we have these 3 headers which are labeled. This one up here, it is labeled FPGA config, and this one being placed in close proximity to these 2 ICs, which are the XCF04 Xilinx in-system programmable ROMs for configuration of FPGAs. These are 4 megabit each, and as I was saying, this header labeled FPGA config will most certainly allow you to load configuration info into these ROMs. As I was saying earlier, that I suspect there is an FPGA on the other side of this board, the labeling on this header further strengthens that belief. We also have this middle header which is labeled boundary scan, and this one right here which is not shrouded and is labeled JTAG. On the right of these headers we have this IC which stands out, and this one is the Intel XT971 ALE, and it's a single chip 100 megabits Ethernet PHY transceiver, and we can see it's placed right next to the RJ45 port, which is actually the Ethernet port on this main board. These 2 smaller ICs in SO8 package, which are placed in close proximity to the Ethernet port, are the LC03-3.3 from Semtech, and these are transient voltage suppressors, which in this case, judging by their location, they're obviously used to protect the circuits associated with the Ethernet port. Moving up, on this RJ45 port, which has the yellow cable connected, we have the RS232 serial port, which is also present on the outside of the enclosure, and right next to it we have this IC labeled SP3232. This one is obviously an RS232 transceiver, judging by its name and position relative to the debug port. And we also have a second debug port which is not going to the outer case. This must be using for some internal debug, and I'm sure I'll be checking this port later on when I try to repair this board. Taking a look at the center section of this PCB, we see this massive BGA LAN pattern, and this is most likely an FPGA on the other side of this PCB. We see decoupling caps placed in a certain pattern right on the backside of that BGA LAN pattern. We also have some op-amps. Some are from analog devices like the AD8604, which is a quad rail-to-rail single supply amplifier. We also have the OPA725 from Texas Instruments, which is also a high-speed rail-to-rail op-amp, and what looks like a bunch of local linear low dropout regulators. I suspect these are linear regulators, judging by the tantalum caps placed right next to these ICs. So most likely these regulators provide local power to some ICs on the other side of this PCB. We also have a couple of genuine bodge wires on this board. We can see one going from this point to this point, and a smaller one right here on this quad op-amp, I believe. It's not uncommon with this kind of systems to find bodges because they sell these in low quantity, they are expensive to manufacture, so it's cheaper to correct errors with small bodges than to respin the entire board, wasting an entire assembled board full of expensive components. So far we haven't seen any of the RF high frequency stuff, so that must be on the other side of the board inside RF cans. So I'm going to continue with the disassembly and see what we get on the other side of the PCB. Overall, the board is nicely laid out, also nicely labeled with test points, and I should be able to check voltages on this board when I start debugging. There's also a label on this lower part of the PCB which says all unnamed test points on this side are ground. So it's quite nice. We have test points, we have labels, you have something to work with. And as I said, I'm going to start by probing the voltages on this board. So enough with this side of the board. I'm going to continue disassembling and see what we get on the other side of this PCB. Now I suspect there are a bunch of board-to-board interconnects on the other side of this PCB, connecting signals from this PCB to the ones which are lower. So I'm going to try to disconnect it with care so I don't bend or break anything in the process. It's either board-to-board interconnects or they're soldered, and I'll have to remove something else. I just noticed I missed this big warning label, warranty void if seal is broken. So obviously there is a screw underneath this label and I need to take that off to be able to remove this board. And just as I expected, we have an application processor from Freescale right where I suspected it should be. A Xilinx FPGA in the middle of the board, exactly where I suspected it should be. And we have some RF happening in here. Obviously not the high frequency RF, but we do have these two connectors feeding signals into these boxes, which most certainly are the receive and transmit sides of the radio for the high frequency. Before discussing anything on this side of the PCB, I'm going to try and remove these top shields to see what we have inside these cans. Up here we have a couple of press-fit board-to-board connectors. The one on the left is labeled TX bias and the one on the right is labeled RX bias. So these two are probably providing control and bias signals to the TX and RX sections, which are in the shielded cans that go in the die-cast enclosure. I have removed the top covers on these shielded cans to see what we have inside, and here is a close-up of the passives inside these shield cans. I have identified right here in the upper side a mixer IC from Analog Devices, and also I have found a couple of budges right inside this can, which can be seen on this picture. Moving away from the shielded cans, we have a pair of TLK 1201, this one right here and this one right here. These are gigabit Ethernet transceivers and they operate at 1.25 gigabits per second, providing up to 1 gigabit per second of data bandwidth over a copper or optical media interface. I suspect the one closer to the fiber module is bridging the FPGA to fiber, and the one closer to the RF cans is bridging RF to FPGA. The FPGA, which is right here, is a Xilinx 3S1500 Spartan 3 FPGA with approximately 30K logic cells inside. Moving down, we have the Freescale MPC 8270, a Power Quick 2 processor with embedded communications processor module, and it's targeted for telecom applications, and telecom is exactly what we have here on this board. The processor will be running our real-time operating systems. We have another press-fit board-to-board connector labeled Synth, which probably is the control and power interface for the synthesizer section, which must be in the lower shielded section. And a set of gold tabs right here on the right, which mate with some press-fit connectors from the main power supply board. This will be the main power entry point for this PCB. So if you remember earlier, when we took the main board out, we were left with this high frequency RF section in these die-cast shields, and after looking around I saw all these screws keeping all the modules together, but I figured this whole section has a top cover, but this top cover is actually screwed from the back. I wasn't going to be able to remove this top cover from the top, and after looking on the sides of these shield cans, I noticed there was some excess thermal paste. So that's when I realized this whole module is actually being held in place by a couple of screws and thermal paste to the actual enclosure. So now I'm going to attempt to remove this RF section, and that should be easy. Alright, so now we don't need these enclosure cover anymore. So as I was telling you earlier, I believe these two gold and this silver plates are going to come off, so we are able to inspect the inside of these high frequency modules. But to do that, I'm going to have to remove all these screws. So after removing a lot, and I mean a lot of screws, I finally managed to open this RF microwave section. So first I'm going to take the cover of this synthesizer section, and I'm going to leave it right next to it because there is something interesting in here. So the first thing we notice is this very small PCB, a double-sided PCB that its sole role is to pass signals from one side to the other. So we have this spring-loaded board-to-board interconnect which passes signals to the bottom side of this PCB, and the top side of this PCB passes signal to another connector just like this, which resides on the main board. Right here at the top of this module we can see the output going into this microwave waveguide, and we have this very small piece, and I'm going to try to zoom in on it. This very small piece, similar to what you find connecting the LCDs in your regular multimeters. So this is the type of material called the zebra strip, and it is used to pass signals from these gold-plated pins to the PCB that sits on top, and it's this one. And some RF magic also happens on here, and here is a macro close-up of this section. This is the best I could get with my camera and macro lens. So something obviously happens at some microscopic level on this small PCB. So let's remove the zebra strip. Now let's see what we have on the other side of this PCB. Well, obviously on this side I forgot mentioning this oven controlled crystal oscillator from Fox. It's precisely 10 MHz with 6 decimal points. And we have some interesting analog and RF microwave stuff happening on this other side of the PCB. This is what I believe goes on this board. We have the ADF4154 frequency synthesizer chip, which takes an input frequency from this voltage controlled oscillator. That frequency is then passed to the Hittite HMC 368LP4, which is a frequency doubler with both input and output amplifier. And this is how our intermediate frequency is created. I believe the IF at this point is between 4 and 8 gigahertz, but once again I don't know much about microwave circuits, so please correct me if I'm wrong. But having the HMC 441 power amplifier on the output of this circuit means we are limited between 6 and 18 gigahertz, and that range is split into different chip versions, and I don't know what version we have on this board, but anyway, those are the outer limits. That frequency might be multiplied again on this small PCB right before entering the waveguide, but I'm not sure, and I can't see much on that small PCB. I just can't magnify it enough to understand what happens in there. So I'm going to move these aside, and I'm going to continue with opening these RX and TX sections. I don't know if I mentioned, but right here on the middle of this waveguide is we have a port that is actually the port that connects this whole section to the actual antenna. So the signal comes in here and is then split, going on the left to the receive side and on the right to the transmit side. Well, actually it happens the other way around. The transmit side is putting signal into this waveguide, and it then goes to the antenna through that port. I'm going to put this section aside. So let's take a closer look at our RX and TX modules. First, let's talk about the RX module. Besides the linear technology 1763, I can't easily identify other components. The PCB looks like a normal one, and that's because this PCB doesn't carry any high frequency signals, so it doesn't need that special substrate that we saw earlier. It is in here just for control and biasing of the actual high frequency circuits. You might wonder where the RF output of the RX module is, and that port is actually connected directly to the hybrid module and goes out through the die cast on the other side of the enclosure. Same as with the previous module, the high frequency circuit is this hybrid placed right in the waveguide channel. Unfortunately, this whole die cast piece is too thick, so I can't look at it in my microscope because I'm unable to focus at that distance. So all I can show you is these macro shots. Next up, here is the TX module, and the same thing can be said about this module. The PCB looks like a normal one because it only hosts some bias and control circuitry, while the actual microwave is handled on the small hybrid module placed in the waveguide itself. Same as with the previous RX module, the actual RF input port is connected directly to the hybrid module through the die-cast enclosure. On the TX module PCB, we can identify 8 LinearTech 1763 low dropout regulators. These are some very low noise regulators, each capable of half an amp output, and seeing 8 of them on this board makes me think each of these is supplying an amplifier / multiplier in the microwave hybrid module, because remember, this thing needs to multiply the frequency up to 80 GHz. Also, here is the best macro shot I could get of that hybrid module. I finished putting all the screws back together, and I have assembled, hopefully like it was before, the high frequency RF module. But before putting it back to the before bolting it back to this backplate, I'm going to add some thermal paste because that's the way it was originally. But I had to clean it when removing it. So I won't use too much. And I'm going to try to spread it to get an even distribution across the surface. That should do it. Okay, so now more bolts to put back together. So now that I finished putting back together the RF section, let's also take a look at this power input board. I have already removed these 3 screws, and as you can see it has a strange shape because they needed to fit the PCB inside this case. So let's remove it. As we can see right here, they're using the die-cast enclosure as a heatsink for these DC to DC converters. So these probably get hot at some point, and they're using the die-cast enclosure as a heatsink. Now on this input power board we don't have much. I mean the power comes in here. We have 3 fuses. They have some input protection in here, and then the power goes to these 2 DC to DC converters, which are integrated on their own PCB. So the thing is, you buy these already assembled and then you just solder them to your power board, and you don't have to deal with all the hassle of designing an efficient DC to DC converter. Let me show you something about this, something interesting about these converters. I have zoomed in into the side of one of the DC to DC converters, and we have some interesting design aspects here. These 3 are inductors, but look at how they are made. The PCB itself is multi-layer, I don't know, 6, 8, maybe more layers, and they are actually using copper traces in a spiral pattern on each layer, this way creating a longer track and increasing the inductance. And then they leave these routed slots so that they can insert the ferrite rings, and this way you have created an inductor with basically just the cost of a ferrite ring, because all the copper is already on your PCB. These 2 converters seem to have an input between 36 and 75 volts DC and an output of 5 volt DC and 10 amps. So in total this whole power board will be supplying the main board with 5 volts up to 20 amps. I'm almost finished putting this whole assembly back together. I hope you liked watching me tear down this antenna plus radio module. I'm sorry I couldn't give you more detailed explanations on the microwave section, but as I work more with these kind of circuits and also get a chance to repair them, I hope to learn more and be able to discuss in greater detail these subjects on future videos. Thank you for watching this video. As always, thumbs up always helps, and see you next time.